In this section, we're going to consider the central metabolic pathways in all of metabolism, and these are glycolysis and gluconeogenesis. If you look at where glycolysis and gluconeogenesis fit into metabolism, you can see that they are very central pathways in all of metabolism, that they link many of the synthetic and degradation pathways in metabolism. Now, the important thing to realize when you look at the whole scope of metabolism and where glycolysis and gluconeogenesis fit in is that glycolysis and gluconeogenesis deal with how the body works with glucose, how it breaks it down, or how it stores it as polysaccharides. Now, glycolysis is the process by which glucose is broken down to pyruvate for oxidation or for further metabolism. Gluconeogenesis is exactly the opposite of glycolysis. It's the process by which a variety of different compounds are converted to pyruvate and then back to glucose, the purpose of which is to keep blood glucose normal in the fasted state. Later on, we're going to consider glycogen metabolism, which deals with the production and breakdown of glycogen, which is the major storage form of glucose, and that's connected very intimately with glycolysis and gluconeogenesis. Now, before we consider this, we have to understand a few basic things about how serum glucose is controlled. Normal serum glucose is controlled within a very narrow range of approximately 70 to 140 milligrams per deciliter at any given time. Now, the serum glucose is maintained by, number one, increased glucose uptake, which occurs in the fed state. So when our glucose concentrations rise, insulin causes the uptake of glucose by the cells of our body to maintain the serum glucose within this normal range. In the fasted state, when the serum glucose starts to fall, then we have increased glucose production stimulated by glucagon in order, again, to maintain that serum glucose within that very narrow range. Now, how do we define increased and decreased blood glucose? Well, when the glucose dips below this normal range, we call that hypoglycemia. And the definition of hypoglycemia is different for males and females. For males, anything below about 45 to 50 milligrams per deciliter starts to cause dysfunction of our bodies, and we call that hypoglycemia. Anything less than about 35 to 40 milligrams per deciliter in females is also considered hypoglycemia. And this is in fact after a fast, so fasting serum glucose. Normal fasting serum glucose is less than 100 milligrams per deciliter, but greater than 40 to 50 milligrams per deciliter. Now, when somebody has a fasting glucose between 100 and 125 milligrams per deciliter, we describe that person as having impaired glucose tolerance. And this is considered in many individuals a pre-diabetic state. Frank diabetes is defined as greater than or equal to 126 milligrams per deciliter of glucose after a fast. Now, the first thing that we have to do with serum glucose is we've got to figure out how to get that serum glucose into cells. And this is a very tightly regulated process. Glucose is transported across the plasma membrane of cells by a family of transporter proteins that have the name GLUT. All of these things are called GLUT plus some number. GLUT1 and GLUT3 are transporters that are present on all mammalian cells, and they're responsible for basal glucose uptake. The Km for glucose is about 1 millimolar, which is lower than normal serum glucose, which is usually about 4 to 8 millimolar. The consequence of this is that glucose is being constantly transported by this transporter into cells. GLUT2 is present only on liver, hepatocytes, and pancreatic beta cells. The Km for glucose for this transporter is 15 to 20 millimolar. So significant transport only occurs when blood glucose is very high, indicative of a fed state. In the fed state, then, glucose enters the pancreatic beta cells to signal insulin secretion. And this is important because we only want to signal insulin secretion in the fed state. That's why it's so important that the Km for glucose of GLUT2 is so high. It also enters the liver because the liver is the key organ in creating the storage forms of glucose, which are glycogen and fat. So what this does is it ensures that glucose only gets stored in excess when the blood glucose is very high. So then when the blood glucose is low, it's preferentially used by the brain and other tissues that need it for metabolism. Now, GLUT4 is present in fat and in muscle cells. Normally, GLUT4 is not present on the surface membrane of these cells, but rather in the membranes of intracellular vesicles. When it's in the membranes of intracellular vesicles, obviously, it can't transport any glucose. But this particular receptor is responsive to insulin. In the presence of insulin in the fed state, there's translocation of this transporter to the plasma membrane. The vesicles fuse with the plasma membrane and allow GLUT4 now to be expressed on the surface of these cells. This allows then excess transport of glucose into fat cells and into muscle cells in the fed state, so that it can be stored then as glycogen in muscle and fat in the adipocytes in the fed state. Now, once we've transported glucose into the cells, the first step in glycolysis is the phosphorylation of glucose to glucose 6-phosphate. Once it's phosphorylated, then the glucose is trapped in the cell. It can't be transported back into the serum. Now, this is the first and most important regulated step in glycolysis. The next 5 steps of glycolysis result in the conversion of glucose to 2 molecules of glyceraldehyde 3-phosphate, which is a 3-carbon molecule. So we've gone from a 6-carbon molecule to a 3-carbon molecule. Now, this is an example of the intermediate steps in a metabolic pathway that aren't important for you to learn for the USMLE. The only step that's important to memorize in this first half of glycolysis are 2 steps that I'll describe in just a minute. The first step we've already talked about, the conversion of glucose to glucose 6-phosphate. Now, in these 5 steps, it takes some energy. It consumes 2 ATPs per glucose molecule to get from glucose to 2 molecules of glyceraldehyde 3-phosphate. The second 5 steps of glycolysis result in the conversion of these glyceraldehyde 3-phosphate molecules to pyruvate. Now, these steps are energy generating. They produce 4 molecules of ATP and 2 molecules of NADH per glucose molecule that's metabolized. Now, before we consider how glucose goes through this pathway, we need to consider a couple of other inputs into glycolysis. And these inputs come from the other monosaccharides that we may encounter in our diet. The first of these is fructose. Fructose is a component of sucrose, which is common table sugar, and it's also found as a monosaccharide in many of the foods we eat, including things like fruits and honey. Fructose is metabolized into intermediates of glycolysis in one of 2 ways. In the liver, fructose is phosphorylated to fructose 1-phosphate by an enzyme called fructokinase. Fructose 1-phosphate then is split to form dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, which are the 3-carbon intermediates of glycolysis. Now, alternatively, when fructose levels are extremely high, it can actually be converted directly to fructose 6-phosphate by hexokinase, which we'll learn about in a few minutes. And then fructose 6-phosphate is a component or an intermediate in glycolysis. Now, there are ways that the metabolism of fructose can go wrong, as illustrated in the following clinical vignette. A 9-month male presents due to difficulty with transition to solid food. He's been breastfeeding and done fine with only mild irritability, but with no significant problems. But once he converts to solid foods, and especially after eating certain types of baby food like fruit, he becomes very irritable with shaking, sweating, and frequent vomiting. His mother notices abdominal distension and jaundice. Further evaluation reveals hypoglycemia, hyperuricemia, lactic acidosis, and increased liver function tests. Urine is positive for particular types of reducing sugars. So the disease that this patient has is hereditary fructose intolerance. Now, there are 2 types of this disease. These diseases we call generally fructosuria, which means that you see fructose in the urine. One of these is very benign, and one of them is very serious. The benign form is essential fructosuria. This is the benign presence of increased urinary fructose, and this is due to a deficiency in fructokinase. It's not a complete deficiency. All that happens is that fructose isn't metabolized very efficiently, and so you get the loss of some fructose in the urine. This is a benign condition, which doesn't lead to any major clinical consequences. Hereditary fructose intolerance, on the other hand, is a severe and potentially life-threatening disease, which is due to the deficiency of fructose 1-phosphate aldolase, or aldolase B. And I'll tell you what that enzyme does in just a minute. This disease is autosomal recessive. It occurs about 1 in 20,000 birds. And what happens is severe hypoglycemia after ingestion of fructose, and that's due to the inhibition of gluconeogenesis in the liver. They also have vomiting, prolonged neonatal jaundice, and hepatosplenomegaly. What happens is that fructose 1-phosphate accumulates in the liver, and this leads to hepatotoxicity. So here's the pathway of fructose metabolism in the liver. And understanding this pathway, you'll see why this disease is such a problem. Fructose is converted by fructokinase to fructose 1-phosphate, which we described earlier. And then this enzyme aldolase B then is responsible for breaking down that fructose 1-phosphate into the 3-carbon intermediates glyceraldehyde and dihydroxyacetone phosphate. These then are converted to glyceraldehyde 3-phosphate, which then enters glycolysis. In hereditary fructose intolerance, remember that it is the aldolase enzyme which is deficient. And when this is defective, then you get a buildup of that intermediate fructose 1-phosphate, and that causes, again, inhibition of gluconeogenesis, leading to hypoglycemia, and is toxic to the liver, leading to the long-term sequelae of this disease. The treatment of hereditary fructose intolerance is restriction of dietary fructose. And this often leads to complete recovery, and if it's controlled in this way, usually the affected adults live a normal life, have normal intelligence, and so forth. Now, what older children and adults are protected from large dietary intakes of fructose by an aversion to sweets, because when they eat anything that has fructose in it, they get very sick, and so they tend to want to avoid those types of foods. If, though, they take very smaller amounts chronically over a long period of time, this can lead to some toxicity, causing reversible growth retardation. So that's how we deal with fructose. The other monosaccharide that we need to consider is galactose. Galactose is a component of lactose. Remember, lactose is made up of a molecule of glucose and a molecule of galactose. Lactose is the type of sugar that we find in dairy products. It's metabolized to glucose 6-phosphate in 4 steps that require ATP and UDP glucose. Basically what happens is that galactose is converted to galactose 1-phosphate, and then it's exchanged with a molecule of UDP glucose, such that you end up with glucose 1-phosphate and UDP galactose. UDP galactose then is recycled to UDP glucose, and you get a little cycle there. So the glucose 1-phosphate then is converted to a molecule of glucose 6-phosphate, which can enter glycolysis. So the net effect is that galactose is converted in this process to glucose 6-phosphate. Now, just like we had problems with fructose metabolism, we can have problems with galactose metabolism as well, as illustrated in the following clinical vignette. A 6-week-old infant is brought to her primary care physician because she's not eating well. When she does eat, she often vomits. Her mother is also concerned because her skin and eyes are becoming more yellow. Physical exam reveals a small, ill-appearing infant with jaundice, hepatosplenomegaly, and some bruising. She has yet to regain her birth weight. When you do some laboratory tests, you see that she has all the sequelae of liver failure. She has elevated liver function tests like AST and ALT. She has a direct hyperbilirubinemia. She has prolonged clotting times, PT and PTT. She has hypoglycemia and hypoalbuminemia. You also detect galactose in her urine. A liver biopsy shows extensive fat exchange with some fibrosis. This patient has a disease called galactosemia. This is hereditary galactose intolerance. Galactosemia is actually the most common disorder of carbohydrate metabolism, with an incidence of about 1 in 23,000 live births. It's caused by a deficiency of galactose 1-phosphate uridyl transferase. Now that's a long name. We also call it GALT, G-A-L-T. This is the enzyme responsible for the interconversion of galactose 1-phosphate and UDP glucose, as shown in the schematic diagram. What happens then, you can imagine, if you block this step, is an accumulation of galactose 1-phosphate. Or, as it builds up, it has a lot of metabolites that accumulate as well. For example, galactitol. The initial clinical features appear very early, within a week of birth, and this is because babies, of course, live on milk and have to be able to consume, absorb, and metabolize lactose. What you see initially is failure to thrive, vomiting and diarrhea, liver failure, which causes jaundice, hepatomegaly, and the coagulation defects that we described, abnormal renal function, including acidosis, glucosuria, and aminoaciduria, and an increased risk for E. coli sepsis. Now, the liver and kidney problems are limited to the first few years of life. That is, if you can control this disease early, usually there won't be any long-term consequences. However, if children are untreated and then survive the initial liver and kidney problems, they develop cataracts from accumulation of galactitol. They may have mental retardation and learning disabilities and ovarian failure in girls. Because the consequences of this disease are so severe, early diagnosis is critical. Almost all states in the United States include galactosemia in their neonatal screening programs. The diagnosis of this disease can be made by the clinical features, the presence of galactose in the urine, and then you have to do an enzyme assay to show that there's a reduction of galled activity in erythrocytes, that is red blood cells. The treatment of this disease is simple. You have to eliminate the presence of lactose and galactose in the diet. So children with this disease have to go on a special diet that contains almost no lactose or the monosaccharide galactose. So far we've considered the ways that the three major monosaccharides in our diet enter glycolysis. Now we have to consider the individual steps in glycolysis itself. Now one general concept that's important to understand is that almost all of the enzymatic steps in glycolysis are reversible. And the direction that these reactions go depends upon the relative concentrations of the substrates and products of those reactions. If the substrates are higher, then it will flow in the forward direction. If the products are higher in concentration, the reactions will flow in the reverse direction. The three exceptions to that are the three irreversible steps of glycolysis. Now these are the rate-limiting steps and the targets of regulation of glycolysis. Now when I say that, what I mean is that these are the three steps that you really need to understand for the USMLE. Now gluconeogenesis is essentially a reversal of glycolysis. It's the opposite of glycolysis. And so we're able to do that because there are three special enzymes which reverse those three irreversible steps to move the process in the opposite direction. Now the first irreversible step in glycolysis, which is the last irreversible step in gluconeogenesis, is the conversion of glucose to glucose 6-phosphate. Now there are two enzymes which are responsible for doing this. One is hexokinase, and this is the one that functions in all cells, or glucokinase, which is a special enzyme found only in the liver and the pancreas. In gluconeogenesis, this step is reversed by glucose 6-phosphatase that takes the glucose 6-phosphate and converts it back to glucose. Now hexokinase, as I mentioned, is found in all tissues, and it has low specificity. In addition to phosphorylating glucose, it can also phosphorylate fructose and phosphorylate galactose to allow these to enter glycolysis. It has a very low Km, meaning that it's saturated at normal blood glucose levels, and it has its maximal rate at normal blood glucose levels. It's on almost all the time. It is inhibited, however, by high concentrations of glucose 6-phosphate. And this is important because it means it's a regulatory feature that allows the cells not to accumulate too much glucose. Remember that glucose 6-phosphate, once it's formed, traps the glucose in the cells. And so by having a negative feedback inhibition of this enzyme, we're able to control the amount of glucose that enters the cell. Glucokinase does exactly the same enzymatic reaction, but it's only found in liver and pancreatic beta cells. Now this has high specificity for glucose, unlike hexokinase, and has a high Km. And this is very similar to, remember, the GLUT2 transporter that's also found in the liver and in the pancreatic beta cells. And like GLUT2, the glucokinase is only active when the blood glucose is high. Now one of the important features of glucokinase is it's not inhibited by glucose 6-phosphate. And so this allows a supply of glucose 6-phosphate for glycogen synthesis in the liver, even when glycolysis is saturated or inhibited. So unlike normal tissues in which we want to control the amount of glucose that enters the cell, we want a lot of glucose to be able to enter the liver cell so that we can store all of this excess glucose as glycogen. And so this ensures that all excess glucose enters the liver and the beta cells specifically. Now, the reversal of this step in gluconeogenesis is glucose 6-phosphatase, converting glucose 6-phosphate back to glucose. Now, this enzyme is found in the lumen of the endoplasmic reticulum, and there are transporters that bring glucose 6-phosphate into the endoplasmic reticulum and transport glucose and inorganic phosphate back out. And this will be an important feature later on that we'll discuss. This enzyme is not found in the brain or the muscle. And so what that means is that gluconeogenesis cannot occur in these tissues. In fact, the most common site of this enzyme is in the liver, which is the major organ for gluconeogenesis in the body. Now the second irreversible step, the second step that you need to understand for the purposes of the USMLE, is the phosphorylation of fructose 6-phosphate to fructose 1,6-bisphosphate. And this is done by an enzyme called phosphofructokinase, or PFK subtype 1, PFK1. This step is reversed in gluconeogenesis by fructose 1,6-bisphosphatase, or FBPase1. Phosphofructokinase is the rate-limiting step in glycolysis. This is the most important step in regulating the rate at which glycolysis proceeds or doesn't proceed in the cell. It's regulated by the energy balance in the cell as measured by ATP. Now, what do I mean by energy balance? What I mean is the general energy state of the cell. We have a high energy balance in the cell when ATP levels are high, and that occurs in the fed state mostly. We have a low energy balance when ATP levels are low. And so when ATP levels are high, you can imagine that you want to negatively regulate glycolysis because you have plenty of energy for the cell. When ATP levels are low, however, you want to upregulate glycolysis to produce more energy. And this occurs by this negative feedback regulation by ATP. When ATP levels are high, this negatively regulates PFK1 and slows glycolysis when there's a positive energy balance. On the other hand, AMP, which is the breakdown product of ATP, which is high in a low energy state, this positively regulates PFK1, increasing glycolysis when there's a negative energy balance or when the energy level of the cell is low. So when ATP is high, we slow down glycolysis. When ATP is low, we speed up glycolysis. And that makes sense for the physiology of the cell. The reverse of that is fructose 1,6-bisphosphatase. And this is, similar to PFK, the rate-limiting step in gluconeogenesis and controls whether gluconeogenesis is happening or glycolysis is happening at any given time. This is also regulated by the energy balance of the cell, but in exactly the opposite fashion to phosphofructokinase. In this case, ATP positively regulates fructose 1,6-bisphosphatase, increasing gluconeogenesis when there's positive energy balance in the cell. On the other hand, AMP negatively regulates fructose 1,6-bisphosphatase, decreasing gluconeogenesis when there's a negative energy balance in the cell. So what you'll notice about this regulatory system is it ensures that glycolysis and gluconeogenesis are mutually exclusive. That is, glycolysis and gluconeogenesis are never going on at the same time. And that makes a lot of sense. Because these are opposite pathways, if they were active at the same time, you would just create a futile loop in which you're breaking down glucose to pyruvate and immediately converting that pyruvate back to glucose through gluconeogenesis. You don't want to do that. You only want glycolysis on at a time when gluconeogenesis is turned off, and vice versa. And so this is one mechanism by which that occurs. Now, glycolysis and gluconeogenesis can also be controlled hormonally by insulin and glucagon. And the key regulator, the key mediator of this regulation is a molecule called fructose 2,6-bisphosphate, or F26BP. This is a key allosteric regulator of both phosphofructokinase 1 and fructose 1,6-bisphosphatase 1. Fructose 2,6-bisphosphate activates phosphofructokinase by increasing its affinity for fructose 6-phosphate and decreasing the inhibitory effect of ATP. So when fructose 2,6-bisphosphate levels are high, phosphofructokinase 1 activity is high and glycolysis proceeds. At the same time, fructose 2,6-bisphosphate inhibits fructose 1,6-bisphosphatase 1 such that gluconeogenesis is inhibited when fructose 2,6-bisphosphate levels are high. Now, fructose 2,6-bisphosphate is produced by an enzyme we call the bifunctional enzyme. This enzyme has two activities in it. One that we call the phosphofructokinase 2 activity, which takes fructose 6-phosphate and converts it to fructose 2,6-bisphosphate, and also fructose 2,6-bisphosphatase 2 activity, which takes fructose 2,6-bisphosphate and converts it back to fructose 6-phosphate. This enzyme is regulated by phosphorylation. When glucagon levels are high in the fasted state, this enzyme is phosphorylated. Now remember, glucagon leads to the phosphorylation of proteins. And that's a general concept that you need to remember for all metabolic pathways. Glucagon, through protein kinase A, leads to the phosphorylation of the bifunctional enzyme. This decreases the PFK2 activity and increases the fructose 2,6-bisphosphatase activity. The net consequence of that is that you have decreased levels of fructose 2,6-bisphosphate. So this decreased fructose 2,6-bisphosphate favors the fructose bisphosphatase activity in gluconeogenesis over the phosphofructokinase 1 activity in glycolysis. So the net result of this is that fructose 2,6-bisphosphate levels are high, inhibiting glycolysis and activating gluconeogenesis. Now this makes sense for the fasted state, because remember, in the fasted state you want to produce glucose to keep serum glucose levels high. And so you want to activate gluconeogenesis to produce glucose and inhibit glycolysis so that you're not consuming glucose. And this occurs in the liver. This is a very important process. On the other hand, in the fed state, insulin levels are high. Remember that insulin leads to the dephosphorylation of enzymes, including the bifunctional enzyme. When the bifunctional enzyme is dephosphorylated, this favors the phosphofructokinase 2 activity, which increases the conversion of fructose 6-phosphate to fructose 2,6-bisphosphate. Remember that high levels of fructose 2,6-bisphosphate activate phosphofructokinase 1, stimulating glycolysis, and inhibit the fructose 1,6-bisphosphatase activity, which inhibits gluconeogenesis. So in the fed state, when insulin is high, the bifunctional enzyme leads to higher concentrations of fructose 2,6-bisphosphate, which activates glycolysis and inhibits gluconeogenesis. And this makes sense also. In the fed state, we want to consume glucose and convert it to storage forms. So glycolysis needs to be turned on. We don't want to produce more glucose because the serum glucose level is already high. And so we want to inhibit the production of glucose by gluconeogenesis. And that's this whole system whereby insulin leads to increased fructose 2,6-bisphosphate and glucagon decreases fructose 2,6-bisphosphate is the key feature of how this whole system is regulated by hormones. Now there's one more irreversible step, and this is the last step by which phosphoenolpyruvate, or PEP, is converted to pyruvate by an enzyme called pyruvate kinase. This reaction generates a molecule of ATP for each of the PEP molecules that's metabolized. Because it's an irreversible step, pyruvate kinase also needs to be regulated. Pyruvate kinase is regulated by fructose 1,6-bisphosphate, which positively regulates pyruvate kinase, promoting glycolysis. This is an example of feed-forward regulation. So in a sense, when fructose 1,6-bisphosphate levels are high, that's a signal that glycolysis is increasing, and it sort of prepares pyruvate kinase for an incoming load of substrate. On the other hand, ATP negatively regulates pyruvate kinase, decreasing glycolysis when there's a positive energy balance in the cell. This is the same concept that we talked about for hexokinase. Alanine, which is a gluconeogenic amino acid, negatively regulates pyruvate kinase, promoting gluconeogenesis. So when alanine levels are high, that's a signal that we should be doing gluconeogenesis and not glycolysis. Glucagon, which remember is high in the fasted state, leads to the phosphorylation of pyruvate kinase, which decreases its activity, promoting gluconeogenesis. And again, these are concepts that we encounter over and over again. Glucagon phosphorylates things and promotes gluconeogenesis. So you can assume then that phosphorylated pyruvate kinase is going to be inhibited. So here's a schematic of gluconeogenesis then. The last step of glycolysis is reversed actually by two enzymes. And so it's a much more complicated process. Part of this process occurs in the mitochondria, and part of it occurs in the cytosol, and it requires a molecule each of ATP and GTP. In the process, a molecule each of NADH and carbon dioxide are moved out of the mitochondria. So we have conversion of pyruvate in the mitochondria to oxaloacetate. Oxaloacetate is then converted to malate. Malate is shuttled back out of the mitochondria, converted back to oxaloacetate, and then oxaloacetate is converted to phosphoenolpyruvate. The first step in this process, the conversion of pyruvate to oxaloacetate, is catalyzed by pyruvate carboxylase, which is a mitochondrial enzyme. Now, this enzyme requires biotin as a cofactor. Now, another general feature that you'll learn in biochemistry is every enzyme which is named carboxylase requires biotin as a cofactor. And you can remember that as a general feature of the function of biotin. This is positively regulated by acetyl-CoA and negatively regulated by ADP. The last step by which oxaloacetate is converted to phosphoenolpyruvate is catalyzed by phosphoenolpyruvate PEP carboxykinase. And this is also negatively regulated by ADP. Now both of these, notice that ADP is a signal of low energy or negative energy balance in the cell. And so remember, under those conditions, we want to favor glycolysis over gluconeogenesis. So it makes sense that ADP would inhibit one of the steps of gluconeogenesis. All right, now there are ways that glycolysis can go wrong, and that's illustrated in the following clinical vignette. A 2-year-old boy with no past medical history is brought for a routine well child checkup. His parents are concerned because he seems to be really tired. You notice when you do a review of systems that he seems to have some exertional dyspnea. He gets short of breath when he exercises or is very active. On physical exam, the boy's tachycardic, he's pale, and he has mild scleral icterus. He's a little bit yellow. The CBC shows a normocytic anemia, and the red blood cells are kind of spiculated when you look at them on a peripheral smear, and he has elevated reticulocytes. Serum methemoglobin is also elevated, which is a clue to this particular disease. The name of this disease is pyruvate kinase deficiency. Now, pyruvate glycolysis is a particularly important process in red blood cells. This is because red blood cells don't have mitochondria. And so the other metabolic processes that we're going to talk about in other sections, the TCA cycle and oxidative phosphorylation, don't exist in mitochondria. Therefore, the only source of energy in the form of ATP and NADH in a red blood cell is glycolysis. Well, what do ATP and NADH do in a red blood cell? There aren't a lot of metabolic processes in a red blood cell. It's a very simple cell. So what does it do? Well, there's two important things that it does. One is the maintenance of proper ion gradients, and the second is the maintenance of iron in the proper redox state. Now, in this schematic, you can see how that functions. There are sodium and potassium ATPases in the surface of the red blood cell. And these shuttle sodium and potassium back and forth between the inside of the cell and the extracellular fluid, that is the plasma. Now, this is important for maintaining the proper osmotic state of the red blood cell. So this process requires ATP also. And so the ATP is consumed in the red blood cell to maintain these ion gradients so that the shape and the osmotic balance of the cell is maintained. NADH, on the other hand, as you can see schematized here, is important for maintaining iron in the proper redox state. So when you have deficiencies in glycolysis, there are basically two consequences. One is that the sodium-potassium ATPase doesn't function well, and this leads to ion imbalances. And when there's osmotic imbalances, the cells either swell or they shrink. And these misshapen cells are recognized as abnormal in the spleen, and they're cleared. And this leads to the anemia that you see in pyruvate kinase deficiency. It also leads to the spiculated red blood cells, which are characteristic of this disease. The other thing that happens is you get a methemoglobinemia. Methemoglobin is a type of hemoglobin that carries iron in the 3+ state rather than in the 2+ state. The problem with iron in the 3+ state is it's not able to bind oxygen. So methemoglobin is not able to bind and carry oxygen. Now, the function of NADH in the cell is to convert methemoglobin back to regular hemoglobin, that is hemoglobin which carries iron in the 2+ state. Without NADH, in the absence of proper glycolysis, the cell isn't able to reduce methemoglobin back to hemoglobin, and this reduces the oxygen carrying capacity of the cell. Now, deficiencies in glycolysis are actually very, very rare. Extremely uncommon. The most common of these by far is pyruvate kinase deficiency, but only a couple of hundred of cases of this have ever been described. Pyruvate kinase is treated symptomatically. You can treat the anemia by giving transfusions and so forth. You can also cure this disease by taking out the patient's spleen. This cures the hemolytic anemia that occurs with the disease. So I want to summarize glycolysis and gluconeogenesis for you. These are the key features of these metabolic pathways that you need to know for the USMLE. The net reaction for glycolysis is glucose plus 2 molecules of inorganic phosphate plus 2 molecules of ADP and 2 molecules of NAD+, which are converted to 2 molecules of pyruvate, 2 ATPs, 2 NADHs, 2 protons, and 2 molecules of water. The key regulated steps in glycolysis, and the only 3 enzymes that you really need to memorize, are hexokinase and glucokinase, which are regulated by glucose 6-phosphate, phosphofructokinase, which is regulated by AMP and ATP, regulated by the energy balance in the cell, and also the key regulator fructose 2,6-bisphosphate, the production of which is regulated by insulin and glucagon. The last regulated enzyme is pyruvate kinase. This is regulated by fructose 1,6-bisphosphate, ATP, alanine, and glucagon, as we described. Diseases associated with glycolysis that we described are pyruvate kinase deficiency. The summary of gluconeogenesis is as follows. The net reaction for gluconeogenesis is almost exactly the opposite of glycolysis, except it requires more energy. So you have 2 molecules of pyruvate plus 4 ATPs plus 2 GTPs plus 2 molecules of NADH plus 2 molecules of water are converted to glucose plus 4 ADPs plus 2 GTPs, 6 molecules of inorganic phosphate, 2 molecules of NAD+, and 2 protons. The key regulated enzymes in this process are pyruvate carboxylase, which is regulated by acetyl-CoA and ADP, as we described, phosphoenolpyruvate carboxykinase, which is regulated by ADP, fructose 1,6-bisphosphatase, which is regulated by the energy balance in the cell by relative levels of AMP and ATP, and, as we described before, by the key molecule fructose 2,6-bisphosphate, the levels of which are regulated by insulin and glucagon, and also glucose 6-phosphatase, which is the other irreversible and major regulated enzyme in gluconeogenesis. This concludes the section on glycolysis and gluconeogenesis.